repeating itself. And it turned out that the golden ratio was an important part of doing that. Fractals, yeah. Fractals, it's all over the place. Remember, fractals are obtained by taking a simple reproduction pattern, and iterating it. For example, you can start with a leaf, and this is meant to be some sort of a leaf growth, and you replace a leaf by 2 babies. If you look at the first one is just a single leaf, then it has 2 children going out the top, and those children are scaled down by a factor. There's a scale factor going up. Then they have children by a factor that is scaled down, and then they have children by a factor that's scaled down, and the scale factor is the same all the time. Now, if you scale them down too rapidly, the thing will just peter out, like a tree that grows and then just sort of dies because there's not enough water. So if you scale them down too rapidly, it just peters out. If you don't scale them down fast enough, you'll find that they start hitting each other and overlapping. If these things are not shrinking fast enough, then they'll start to overlap. In between dying out and overlapping and making a mess, you can find a pattern where things just about touch but not quite. Guess what the ratio is that makes that happen? It's the golden ratio. The golden ratio is the difference between dying out and too much growth that you overlap. Now, that's a cute one. That's a beauty. And here's another example of these patterns. If you want to end up with this beautiful thing that looks like one of those rugs in University Avenue, in those endless rug shops that we have down University Avenue, the growth pattern, the ratio between each generation and the next, the one that makes this beautiful so you don't get overlapping and you don't get dying out, is the golden ratio. Yes?
Question, but is there anything